Hi everyone, my name is Yuhong and I'm presenting our work Algorithmic Collusion at Test Time, a metagame design and evaluation. This is a joint work with Dan and Xingtong at Rutgers. Algorithmic collusion is an economic phenomenon in which competing firms use algorithms to make economic decisions, but the algorithms interact in ways that lead to anti-competitive or collusive outcomes, such as higher prices without human-level communication. Algorithmic collusion has been observed in several real-world scenarios, such as dynamic gasoline pricing and e-commerce platforms like Amazon Marketplace. In these settings, collusion emerges within a limited number of updates. On Amazon, for instance, prices can be updated every 15 minutes, which corresponds to roughly 3,000 updates per month. This leads us to our essential question: can algorithmic collusion emerge at test time among rational algorithmic choices? To study this question, we limit the time horizon of the evaluation and take the cost of exploration and learning into account. We consider realistic scenarios with asymmetric economic settings, such as cost and product qualities, and asymmetric algorithmic choices, including hyperparameters and initializations. Finally, we assume the algorithm adopters are rational and will try to choose the best strategy against their competitors. To understand how we assess algorithmic collusion at test time, it helps to build this framework from the ground up. At the very base, we have the initial policy that determines the move to be made conditional on the initial state of the game, like the current prices set by all participants. These initial policies are typically pre-trained with established algorithms under symmetric settings. We consider pre-training with Q-learning, UCB, and LLMs. It has been shown in previous work that these algorithms can lead to collusion at the convergence of interactions between symmetric players. We use the converged policies as the initial policies for the test time game. Moving up one level, we organize these initial policies into initial policy categories. We evaluate and categorize these policies along two dimensions. The first is the propensity to collude. That is, how likely is this policy to cooperate with a partner it interacted with during its training phase? And second is the robustness against the best response. Would it sustain cooperation if an opponent plays a best response policy against it? This brings us to the strategy layer. A strategy is the specific combination of two things: an initial policy sampled from one of our categories, paired with a specific adaptation rule, such as a learning rate. Zooming out to the meta strategy, as the space of all possible strategies is infinite, we cannot simulate interactions or compute equilibria over an infinite set. Therefore, a meta strategy groups similar continuous strategies into a bounded discrete set. This abstraction allows us to conduct a metagame. A metagame simulates interactions among strategies sampled from meta strategies. Metagames can then be used to collect statistics, including the payoff matrices, for equilibrium analysis. To address our question on whether collusion arises as a rational outcome at test time, we conducted metagame analysis on diverse settings spanning Q-learning, UCB, and LLMs, including players of different cost structures, and initializations that encode optimistic or pessimistic beliefs about their opponent's intent to collude. We can visualize the payoff matrices of these metagames using best response graphs. For example, here we show the best response graph for the Q-learning-based meta strategies. As you can see, there are two pure strategy Nash equilibria in this setting. By analyzing these pure or mixed strategy Nash equilibria, we reach the following conclusion: collusion can be an equilibrium outcome at test time, but diminishes under shorter interaction horizons, asymmetric cost, and pessimistic initialization. Please scan the QR code to learn more. Thank you for listening.